Higher Physics Notes, Unit 1, Section 2, Forces. This is Part 4, another application of Newton's second law. This one involves tethered balloons. So it's the tethered balloon problem. So here's the situation. We have a helium-filled balloon. It must be helium-filled, or at least be a hot air balloon, in order to have an upwards force called an upthrust force. Otherwise it wouldn't float in the air. And it's tethered or tied to the ground with a rope. Tethered is an old English word for tied. So as you can see, it's tied to the ground. So that situation diagram, which I'm calling diagram number 1, is the balloon tethered to the ground. Now the balloon, remember, is less dense than the air with the helium inside it. So it's the balloon's trying to go upwards, and therefore it's putting the rope under tension. So if you were the ground, you would feel a tension force pulling you upwards called T, as shown in the diagram. And if you were the balloon, you would feel the ground kind of reacting to that and pulling you back with T dash, the equal and opposite force to T. So you end up with a situation very like the two people pulling the rope, person A, person B type thing, where you've got T and T dash, the tension running through that rope. Now typically in these problems, what happens is this. You begin with the rope tethered, but then what happens is the rope snaps, or it's cut loose or released, something of that nature. So you then move to this situation, where the rope sort of snaps. Okay. Now, of course, once it snaps, the tension can no longer exist. So there is now no downwards tension force pulling on that rope, and therefore pulling on the balloon. So the balloon will float free and move upwards. So what we're going to do is to analyze this situation and do some calculations using Newton's second law. So that second diagram then is the balloon untethered. And it moves upwards. So there's the scenario. Let's now pose a problem and I'll show you how to solve them. So here is a typical question. A helium-filled balloon is tethered to the ground as shown. We'll see the diagram in a minute. Its mass is 80 kilograms. And the tension in the rope is 1,000 newtons. The rope now snaps. Find the acceleration of the balloon. Right, so here is our sort of situation diagram at the beginning. You can see the balloon there, and it's always worth sketching the situation diagram. It helps you envisage what's actually going on. We know there's 1,000 newtons of tension in there, and we could maybe add the mass of 80 kilograms in as well. Now, it, I hope, is obvious that if the balloon is tethered, then it is at rest. And that's important, as we'll see. So there's the scenario. What we now need to do to solve it, to find the acceleration once the rope snaps, is to begin with a free body diagram for the balloon when it's tethered. So stage one of our solution is to draw the free body diagram of the balloon in its tethered state. Well, the forces down the way are the weight. Don't forget the weight. It's amazing how often people think the balloon doesn't have any weight, but real balloons have often quite considerable weight. But it's not just the weight pulling the balloon down, there's also the tension. So you've got these two forces downwards of weight plus tension. Now the only force up the way is a force that's called upthrust. That's the force which makes things float if their density is less than the density of their surroundings. So that's why polystyrene floats at the swimming pool, float upwards, for example, and it's why hot air balloons float. So there's a free body diagram. Let me remind you that this is at rest. Now, if it's at rest, we can say the forces are balanced. And if they're balanced, then that means that the upthrust up the way must be equal in magnitude to the weight plus the tension down the way. Now notice that in the free body diagram I've written the names of the forces out in full, but once I put these into an equation I use the symbols for convenience. Now at the moment we don't know what the upthrust actually is, but we do know it equals the weight plus the tension, so we can find it out. Well, what are we told? We know the mass is 80, so we can put in that that is 80 times 9.8. We don't need the sign convention here. It's generally pretty obvious from the context what the direction is. And the tension, we're told, is 1,000 newtons. Okay. So that means the upthrust then is 80 times 9.8, 784 plus 1,000. So the upthrust is 1,784 newtons. Okay. Right, so we've got the upthrust. Now we're not finished yet because we actually want to get the acceleration. So we now need to move on to stage 2, which is the scenario whereby the rope has snapped. So we need to draw the untethered situation now, and that's the free body diagram, that is. So that will be this. So now, what do we have? Well, we've got the weight down the way, That's still there. But because the rope has snapped, we do not have any tension anymore. So it's just the weight down the way. The up thrust, of course, is still there. Okay, it's not changed. Nothing's changed at all about the up thrust. Now that up thrust we know is 1,784 newtons. The weight itself is only 784, so we know the up thrust is bigger. So there is indeed going to be an unbalanced force up the way, which will lead to an acceleration, and that's what we're now going to find. So we now know that the forces are unbalanced after the rope snaps. So we can apply Newton's second law. And A is the only unknown. Well, the unbalanced force is simply the up thrust minus the weight. And we now know both of these. We know the up thrust is 1784. And we've already worked out the weight to be 784. So that's going to equal the mass of the balloon, which we said was 80 kilograms, times A. And the rest is just arithmetic. So the unbalanced force is 1,000 newtons. And that's 80 times A. Okay. I don't know if you've spotted it, but it's no coincidence that the tension is 1,000 newtons, and once the tension is removed, the unbalanced force becomes 1,000 newtons. And that's because it's the addition of the tension which balances the situation. Without the tension, which is what we have here in stage 2, the unbalanced force is 1,000. Okay, and that's just an observation. So the acceleration is 1,000 over 80, so that's like 100 divided by 8, giving an acceleration of 12.5 meters seconds to minus 2 upwards. Now we're not using the sign convention, but we do need to specify direction in our final answers. So there we have it. That is how you work out the acceleration for an untethered balloon, which was previously tethered. I've omitted any frictional forces here. Very often we do, but it is theoretically possible you could be told there is a bit of friction. You would have to then add that on to the downward forces in your free body.